All right, so today we're going to be looking at related rates. This is a big topic for your calculus class, so we want to make sure that we know how to do it. And here we go. Suppose x and y are both functions of time. Then x plus 3y equals 5 is how the functions are related. So if x and y are both functions, this expression right here is a relationship between those two functions. Okay. Let's find an equation that describes the relationship between the rate of change of x with respect to time and the rate of change of y with respect to time. So if I take the derivative of this implicitly, I get dx dt. Remember, because x is a function of t, and then 3 dy dt equals 0. This is how the rates are related. So this is why it's called related rates. Okay? How do we solve these problems? Let's take a look. I got it all laid out here for you. It's going to be word problems, so you have to first understand the problem. You can do that by drawing a picture if it's possible. Label the parts with variables / constants. Okay. Identify the rate you are seeking and any rates that you know. You want to write an equation that relates the variables. That's this one up here. Find an equation that relates these variables. And then you can use a lot of times they'll talk about like a geometric figure, like a rectangle, a triangle, a circle, or a cone, or something along those lines, depending on if it's three-dimensional or not. So use that formula. Okay. Do not plug in numbers yet. This is the biggest mistake people make at this point, is they want to get this equation, they start plugging numbers into it. You do not do that. Once you have your function relationship, we're going to take the derivative with respect to time. Okay, to get the related rates. Then, after I have that equation, then I'm going to start plugging numbers into it. I'm going to plug in all the values that I know for every variable that's in that related rate formula. Okay, if there is a value in there, a variable that I do not know, and it's not the one I'm seeking, then I'm going to need to go find a value to plug in there. A lot of times that requires us to go back to the original function, the original expression up here, and then find the appropriate unit, the thing that I need. And then lastly, we're going to do is we're going to solve for the rate that you are seeking and interpret it in context with the appropriate units. So this is what we're going to be doing. So let me show you a couple problems as we go through this, and I'll show you how simple this might be. So we're going to do the first one is that one right there. The rectangle is undergoing change to its length and width over time. Find an equation that relates how the perimeter of the rectangle is changing over time. If you were given a geometric shape, draw the shape. Label the shape with the known variables that you know for the shape. This is a length, this is a width. You can use different letters too, it doesn't matter. If you do base and height, it's the same thing. And then, so that was an important word. The other one is perimeter. That is the key word that you're going to use to find your function relationships. In other words, L and W are like functions of time, and I need to have something that relates these two letters, and that's the word that does it, perimeter. What is the perimeter of a rectangle? The perimeter of a rectangle is 2 lengths plus 2 W's. Okay? So now I have my equation. The next thing I need to do is I need to take the derivative of this equation implicitly with respect to time. The derivative of P with respect to time, and use this form of the derivative. Do not use a prime action. So dP dt equals the derivative of this with respect to time 2 dl dt plus 2 dw dt. And that is our related rates formula. Find an equation that relates how the perimeter of a rectangle is changing over time. This is the perimeter changing over time, and this is the formula or equation that does that. This is the related rates equation. Okay, let's go to the next one. In that one, it says find an equation that relates how the area of the rectangle is changing over time. So same picture. I'm not going to redraw the picture. We have length and width. And what is the formula for the area of a rectangle? So then you write that formula down, length times width. And then I am looking for the change of the area over time, which means I now need to take the derivative with respect to time. So then in this one, I have dA dt equals, and then this is a product rule. The first times the derivative of the second plus the second times the derivative of the first. And that is my related rates equation. Okay, continuing on. Suppose x and y are both functions of time, t, where they are related in this fashion. Find the equation that describes the relationship between their rates. Same thing again. This is the relationship equation. And when I want to take the derivative of this to see how the rates are related with respect to time, the derivative of x squared with respect to time is 2x dx dt. Don't forget your little chain rule action, right? X is a function of time. You need to have that right there. And then we have plus 3 dy dt equals, and the derivative for a constant is 0. And there you go. It is that simple. One more, finding this equation. A circle is undergoing changes to its radius over time. Find an equation that relates how the area of the circle is changing over time. So I need to find the area of a circle. So you have your circle. You have the important variable r in my circle. And the area of the circle is pi r squared. These are all the things you got to start off with. Draw the picture, label it with a variable, and write the starting equation down based off of, in this case, the area of a circle. And now I can take the derivative of this with respect to time. dA dt. Remember, pi is a constant, so I'm taking the derivative of that, which is going to be 2r, lower the power by 1, times dr dt. And there you go. So this is the first part of a related rates problem. Picture, variable, starting equation, and then take its derivative for a related rates equation. Okay, so let's look at the next question here, and now we're going to start doing the next part of this. Okay, a length of a rectangle is increasing by 3 centimeters per second, and the width is decreasing 5 centimeters per second. How fast is the perimeter of the rectangle changing at the instant the length is 10 centimeters and the width is 8 centimeters? A lot of stuff going on in here. The process in the start is exactly the same as what we did in the very first one, where we first did the perimeter up here. Draw a picture. We have a rectangle. There is a length. There is a width. I write down the perimeter equation because that's what they're talking about, the perimeter of the rectangle. So P equals 2L plus 2W. All I'm doing now is just writing things that I know. What else do I know? Are there any rates that I know? Because you're going to need those. And so over by my picture area, I know that the length is increasing by 3 centimeters per second. So the rate of a length is dl dt. So they gave you dl dt. In this case, that is 3 centimeters per second, because it's increasing. I also know that the width is decreasing 5 centimeters per second, so that is dw dt is minus 5 centimeters per second because it is decreasing. Okay? So now what? I have these numbers over here. These values of these things where it says in the instant of those numbers are the last thing you deal with, the very last. So the instant, you never plug those in until the very end. Just make a note of that so you do not forget. But we know there that L would be 10 if I need it, and W will be 8 if I need it. So these are small numbers over here that we use last. Once I have all this information right here written down for my problem, then I can take the derivative of this with respect to time. dp dt, 2 dl dt, plus 2 dw dt, and this is the equation I plug into. The reason why I say you never plug these numbers in to begin with, because you'll notice, since this is the equation I'm going to plug into, there is no L and no W over here. These are irrelevant. They are not part. You're not going to use those at all. Okay. I need to find the change in the perimeter. Okay. How fast is the perimeter changing in this instant? Well, it's changing exactly the same all the way around. It's never matter what instant it is. At every instance will be changing exactly the same way. And so you just need to plug in the numbers you have, which means dp dt is 2 times 3 plus 2 times negative 5. And so that gives me negative 4. So now we need to interpret this in context of this problem. Okay? So the answer is the perimeter is decreasing by 4 centimeters per second when L equals 10 centimeters and W equals 8 centimeters. Yes, I use those in my final answer because that's what I wanted they asked you to use. But they don't play a role in this finding of this number. Okay? Just in the final answer part over here. Sometimes those numbers will play a role, so don't stop writing that stuff down. They're not always going to be irrelevant. Just in this case, it did not matter what those numbers were. And so there's that question right there. Let's do another one. The length of a rectangle is increasing by 3 centimeters per second, and the width is remaining constant at 5 centimeters. How fast is the area of the rectangle changing at the instant the length is 10 centimeters? Again, you just do it exactly the same way every single time. You do not deviate. You do not change. Length, width. The area of a rectangle is length times the width. They told me the length is increasing by 3 centimeters per second, so that means dl dt is 3 centimeters per second. The width remains constant at 5. So what is dw dt? If it's constant, the derivative of a constant is 0. And then over here we know we're going to be using at L equals 10. Okay? So that's important over here. And a lot of times it might help if you just write the word at. So all this is going to happen when L is 10. Okay? I'm ready to go. Take your derivative. I've written down everything that I knew. And so we have what? The first times the derivative of the second plus the second times the derivative of the first. And we're looking for the rate of change of the area. So I need to plug in all numbers for all of these things over here. So dA dt, L is 10, but dW dt is 0. W, well, I don't know W. Or do I? Yes, I do. It's 5. It remained constant. So over here I knew that W was 5. I forgot to write that down. So now I have 5, and dl dt is 3, giving me 15. Okay? So the area is increasing by 15. Now, what kind of units would I have on the area? Well, what is the units for area in this case, since we're using centimeters? The area unit is centimeters squared. So this is increasing by 15 square centimeters per second. Okay, when the length is 10 centimeters. So that is how you answer that question. Okay, so those are some basic ones right there. Let's look at, and sometimes you'll get those kind of questions on the AP exam in the multiple choice section because they're fairly quick and easy and you can do them pretty quickly once you get used to them. Here's another one a little bit more advanced. Okay, water is poured into a cubical tank at a rate of 20 cubic inches per minute. Each side of the cube is 5 inches. How fast is the depth of the water changing? Okay, a little bit more involved on this one. So again, as in all things, we write and draw a picture. So do your best to draw a cube. Usually I just do a square like that, line out. All these are parallel, same length. Then draw that, connect it, draw that down, connect it, cube. It is a cube. Each side of the cube is 5 inches, so I don't need to put letters in here, although I can. This is the length, which is 5. This is the width, which is 5. This is the height, which is 5. Okay? But then I have this water level. Okay? And that height right there, I'm going to call, let's just change some of these things around here. I'll just call it D for the depth of the water. Okay? How deep is the water? I know that the water is being poured in at a rate of 20 cubic inches per minute. So cubic is the key here. This is dV dt. The volume is 20 cubic inches per minute. Okay. So I need to find, so now I can't use the whole cube because the water is not the whole cube. Okay. This water is a different height or depth here. But what is the volume of the water? What is the volume of the water? This is for the water volume. Well, the volume of a rectangular prism is the area of the base times the height of it. So that is 5 times 5 times d. So then my volume is 25 times d. So then what? Take the derivative of it with respect to time. So the derivative of the volume with respect to time is 25 times the derivative of the depth with respect to time. See how I did that? So instead of having 2 dd, I just put the second d in the parentheses so know that it's the variable thing. And then what am I looking for? I'm looking for that, right? I'm looking for when this thing, the rate of change of the water. How fast is the depth of the water changing? So I'm looking for that. That means I have to have a number for every other variable, which I do. So this is 20, 25 times the derivative or the rate of change of the depth. So the rate of change of the depth with respect to time is 20 over 25, which is 4/5. Okay. Now, this depth is a single unit. Volume is a cubic unit. Area was a squared unit. This is a single unit. So what are the units on our answer over here? Well, they're all in inches. So this is 5 inches, 5 inches, 5 inches. This is in inches. So this is going to be inches per minute. And so that would be my answer for this one. And you can write it out in the sentence format. The depth of the water is changing. See how I use the sentence to answer the question? At a rate of 4/5 inches per minute. All right. Let's look at the last example I have here. Sand is piled into a right circular cone at a rate of 8 cubic feet per minute. The radius of the cone is equal to its height. How fast is the height of the cone changing when the height is 5 feet? So they use this one a lot because in the real world, if you make a pile of dirt or something like that, and you make it, steadily drop the dirt into a big pile, it will form a cone, a right circular cone. That's what it does. So I have basically something that looks like that. Down here, from the center out, that is your radius. From here, that is the height of the cone. Okay? And so that is a picture of what our cone looks like. We want to find the volume of a cone. The volume of a cone, if you do not know it, make sure you know these formulas. 1/3 pi r squared times h. The area of the base, pi r squared, times the height. And then cones and pyramids get a 1/3 in front. So that is the formula we're going to start off with. What else do I know? I know that the sand is being piled at a rate of 8 cubic feet per minute. So that is dV dt, and that is 8 cubic feet per minute. What else do I know? The radius of the cone is equal to the height. That's nice to know because it helps eliminate one of my variables. I know that the radius is equal to the height. Okay? What else do I know? I'm going to do this. How fast is the height? That's important. Of the cone changing when the height is 5 feet. So I'm going to look at this at h equals 5. Now the reason I write this down over here, and I talked about the height, is because my formula up here has radius and height, and r equals h. So this tells me that I want to change the r's to h's, not the other way around. Okay? I could ask a different question about the radius, and then you would change the h to an r and do the problem again. So I'm going to rewrite this equation. 1/3 pi. R's become h's, so that means that's h squared times h, which makes this h to the 3rd power. And so that streamlines our formula down before I have to do the derivative. You could have taken the derivative with respect to time of this here, using the product rule and all that kind of stuff. It could have worked. It will work out. And you would just have to go and take the derivative of this down here so you can see the relationship between dr dt and dh dt. Now, once I have all this information laid out, I can now take the derivative with respect to time. That's a constant. So it's that quantity times 3. So pi over 3 times 3 times h, lower the power by 1, times dh dt. I need to have a value because I'm looking for that. I need a value for dv dt and a value for h. So plug all that in. 8, this is pi, because those drop out, times 5 squared dh dt. So what is dh dt? Well, it's 8 divided by 25 pi. So it's going to be 8 divided by 25 pi. And h is a unit of length. Okay, so that means it is going to be feet per minute. And that is how fast it's changing. And you can say, again, a sentence format, you can say the height of the cone is changing at a rate of 8 over 25 pi feet per minute. At the instant, h is 5. So that's how I would write that sentence out. Okay, so if you have any questions about this, make sure you bring them up in class and we'll do some more problems.